Hello everyone. In today's video, we will be talking about the electronic structure, especially for the 3 points, the electron box notation, the free radicals, and the ionization energy. So, as we saw in last lesson, that the electronic configuration can be represented by using the notation 1s2, 2s2, 2p6, and so on. And also, there exists another notation which is called the boxes notation. And before explaining this, it's worthy to note, as you can see here in this image, that the electrons can be represented by small spinning charges which rotate around their own axis, either clockwise or anti-clockwise directions. And we mention here that the electrons with the same spin, they repel each other, which means that if we want, for example, to fill one orbital with two electrons which have the same spin, for example, plus 1/2, they will repel each other. This is actually why we will be filling the orbitals with two electrons which are pointing in different directions in a way to minimize the repulsion. So as you can see here in the example of the electron configuration of oxygen, the first orbital will be filled with two electrons, one pointing up and the second one pointing down. 2s orbital will be filled also with two electrons, as we said before that the s orbitals can hold up to two electrons. Then here the first one is pointing up, then the other is pointing down to minimize the repulsion between them. And in the p orbital, we will be starting filling the px with one orbital, the py with one orbital, the pz with one orbital, then the remaining orbital will be filling the px, but in this time it will be pointing down, which means that one is pointing up, the other is pointing down in a way to minimize the repulsion between the electrons. Now let's see the free radicals, and by definition a free radical is a species with one or more unpaired electrons. For example, here is the example of chlorine. Chlorine free radical has the electronic configuration which is the following one: 1s2, 2s2, 2p6, 3s2, 3p6. If we want to represent this electronic configuration using the box notation, it will be something like what you see here: 1s2, 2s2, 2p6, 3s2, 3p5 here. And actually, in the 3p orbital or subshell, there are 5 electrons. We will be filling the px followed by py, then pz, then we complete filling px with the fourth electron and py with the fifth one. Then the pz is actually containing only one electron, and this electron is an unpaired electron. So the chlorine atom can be represented like this: Cl with a dot, and this dot actually is showing this free electron or this unpaired electron here, representing the chlorine, as so we are representing the free radical of chlorine. Okay, and let's see now the ionization energy. As you can see here, we refer to it by the word IE, and actually it's the energy needed or required to remove 1 mole of electrons from 1 mole of gaseous atoms of an element to form 1 mole of gaseous ions. The ionization energy is measured under standard conditions, and its unit is the kilojoules per mole. Here we can define the first ionization energy, IE1, as the energy required to remove 1 mole of electrons from 1 mole of atoms of an element to form 1 mole of 1 plus ions. For example, the first ionization energy of calcium is this one, which means that we will be removing 1 electron from the calcium atom in its gaseous state to form the calcium cation or the calcium ion in its gaseous state. The second ionization energy will be the energy needed to remove 1 electron from the cation Ca plus to form Ca2 plus, and this is called the second ionization energy. If we want to do the third one, we will be removing 1 electron from the cation Ca2 plus in a way to form the cation Ca3 plus, and so on. So we can continue removing electrons from an atom until only the nucleus is left. We call this sequence of ionization energies the successive ionization energies. I hope this was helpful for you. Please don't forget to share, like, and subscribe, and see you in next video.